Okay, let's talk. Let's talk about model fit, and hopefully this won't take too long, because, well, it's not as fun as using the on and the with statements. I mean, is anything as good as that? It's pretty good. But we only made sense of some of the results, right? As we scrolled down in the Mplus output, we got some information about, estimation and whatever else. Then it gave us fit statistics. And then, model fit, this information. And then we just blew right on through that and went straight to the slopes, to the on statements, and the p-values. Some people just went straight to the p-values. And that's fine, you would be forgiven. That's, the system motivates that kind of orientation. And then, and the with statements. But how do we know that those estimates are any good? Remember, earlier we said that what maximum likelihood estimation does is it gives you the best estimates that it can, right? For the unknowns, given the observed data and a bunch of assumptions. But maybe the best estimates aren't very good estimates at all, right? If you show up, you're going to do a renovation on your house, and you ask the person who's put in a bid. I don't know why I'm using this example. You put in a person that's put in a bid, and you say, how's the work personship? Is it any good? And this person says, it's the best we can do. Like, okay. Well, is the best you can do any good? And they're like, well, it's the best we can do. They're like, all right, I'm going to need some more information, right? So what we've basically been doing is we've been taking that person's word for it, that it's the best they can do, and hey, that's not so bad, that's pretty good. We're going to need some kind of outside or some source of information that can help us adjudicate, can help us figure out whether or not the estimates that we were getting, the slopes, the on statements, whether or not those should be trusted. There are a wide variety of different ways to do that. People are bringing up very reasonable concerns about, well, maybe you're making a causal inference that isn't justified based on the data and the model and whatever else. Okay, that's a good point. Fit statistics aren't going to help us with that, but they will help us with various kinds of gross misspecifications of the model. And what we mean by that, we'll talk about. And it probably shouldn't say selection and equivalence and whatever. Mostly we're going to talk about model fit, and then I'll mention modification indices. So now that you know how to use Mplus for path analysis, you should have something to say about the fit statistics. Because when you report results, some of the results that you're going to want to report probably have to do with the fit of the model. Maybe you're going to want to compare different models that you're estimating. You need to know how to do that. What's the rationale for the model comparisons? We're going to provide just a little bit of information on this point. I can see some repeat faces in here that I've seen before in years past. And if you didn't like the way we did it last year, which, I mean, basically nobody likes this. And that's partly my fault. I know for sure, like but it's not entirely my fault. And so what I've tried to do is revise it to make it less my fault and more the fault of the material. But, well, you'll see. You'll see if it's any good. And if you have, if you're in here for the second year, you can tell me what you think. If it's any different or better. Okay. So, model fit. Well, what do we mean by that? There's a ton of literature on model fit, how to understand it, how to make sense of it, how to estimate it. Different communities of researchers understand this concept in different ways, sometimes fundamentally different ways. Some of them have very different interests. We're going to operate from kind of within a structural equation modeling, CFA, path analysis, community approach to model fit, but that's not the only one that you can adopt. For example, if you're in finance or economics or whatever, and you're into forecasting, specifically forecasting, then the way that you understand model fit is going to be very different than what we're going to do. The way you understand things like fit in forecasting, for example, is based on things like out-of-sample predictions, and well, probably mostly that. But that's not what we're going to do. We're going to do something else. If you want a crash course in how the SEM community understands model fit, there are some classic works here. You can see there's a special issue of the journal Personality and Individual Differences, which is a just fine, A-OK, no problem personality journal. So if you're not a psychologist, and that would be a fine resource. It's just fine to get you into the language and the logic there. You'll see it's relatively straightforward. For the most part, people are citing papers like Hugh and Bentler, which has got God only knows how many citations at this point, 20, 30,000. I think I've got it here somewhere. We're going to have a couple of different kinds of fit statistics that we're going to look at. And so you should know that these terms exist because if you go into the fit literature, for SEM, people use these terms. Some kinds of fit statistics, they'll call them absolute fit statistics or fit indices, absolute fit indices. And that's one way to think about these kinds of indices is that these indices tell us how well our model fits the data, the observed data, kind of directly. But that's not the only kind of fit index that we've got. We've got relative or incremental or comparative fit indices. And these give us a different kind of information. The observed data are always there, informing the fit indices that we get, but there are different ways that we can make comparisons. We can compare the fit of different models using the same data. And that might actually be better. If we're, as you'll see, if you want to appear great, then do you want to compare yourself to someone who is also great, or do you want to compare yourself to someone who is not so great? On a relative basis, right, you probably want to go with a more flattering comparison if your goal is to look as good as possible, and the same is true for our models. If we're just comparing the fit of the model to the observed data, well, it's easy for the model to not fit the observed data very well. So what we might want to do if we wanted to cheat a little bit, which is what the SEM community does all the time, is not really cheating, it's just, they got their reasons. But in order to make their models that they want to estimate and they don't want to reject their models, they want to hold on to those models and interpret the slopes and get the p-values and everything else, we might want to compare our estimated model to a model that isn't so good. And so we can do that in various ways. There are also other kinds so those are relative or comparative fit indices. We can also derive what are referred to as information criteria. These have a kind of information theoretic foundation, and they're useful for different kinds of things than these other fit indices. They measure information entropy, or how much information you lose, for example, when you go from one model to another, or from the data to your model. Okay, Bayesians have less work on the topic, but Mplus does give you some fit statistics or information criteria when you use the Bayes estimator, but for the most part, all the literature is on ML estimators or frequentist estimators, so for the most part, we'll just go based on those. So if you're going to use a maximum likelihood-based estimator, what kind of information do you have for informing the model that you estimate? Well, you've got all the observed data, right? And based on the observed data, you're going to estimate your unknown parameters. So how many parameters are implied by our data? This is kind of an interesting way to think about this, our sources of information for estimating the unknown parameters that we estimate, and how those relate to the models that we actually estimate. Well, if we have k variables, whatever k is, let's say we have 10 variables, so k equals 10, then how many means do we have? How many means in the data set will we have? 10. Each variable will have one, right? How many variances in the data will we have? 10. Each variable will have a variance. If we're assuming normally distributed, right, continuous normal distributions, each variable has a 2-parameter distribution, and each variable has a covariance with every other variable. So how many covariances are there? Well, it's k times k minus 1 divided by 2. So that's 10 times 9 which is 90 divided by 2 is 45. There would be 45 covariances there. So you can think of your observed data, if you make the assumption that they're normally distributed, that that's the information they give you. That's all the unique information. Right? Just with that information, you can describe the whole data set, at least statistically in the aggregate. How many parameters are you estimating in your model? Well, what do we estimate? Intercepts, variances or residual variances, and we estimate slopes or regression coefficients, and we estimate covariances. Those draw on different kinds of information. We use different information to estimate those. The intercepts are estimated based on the means, the observed means, right? The variances or residual variances are estimated based on the observed variances, and the slopes and the covariances are estimated based on the observed covariances. That's one way to think about this. So the difference between the parameters you estimate, the number of parameters that you estimate, and the number of the amount of information, the parameters that the observed data have to offer you for model estimation, the difference between those two things is our degrees of freedom, or DF. As the degrees of freedom go up, it's like saying that we're, although I guess there are a number of ways to think about this. One way I've always liked to think about it and explain it is that as the number of parameters we estimate goes down in relation to the amount of information that data have to give us to inform model estimation, as degrees of freedom go up, what we're doing is, it's like we're using less information from the data to estimate our model. It's going to give us a little wiggle room there in various ways in terms of misfit, but well, what about our data and model fit? How are those things related? Well, for maximum likelihood, we have a number called the log likelihood, or the likelihood, for the model that we estimate. And that is actually, it's a probabilistic concept that relates the model to the observed data. And it turns out that if you take the log likelihood value and you multiply it by -2, that has a chi-square distribution, conditional on certain assumptions. And it turns out that, of course, that the difference between two chi-square values is itself chi-square distributed. So that's pretty useful. Every model has a likelihood value, and then we can turn that likelihood value into something that has a chi-square distribution. And the difference between two chi-squares itself has a chi-square distribution. So how are we going to use this information here? The idea of degrees of freedom, the idea of chi-squares, and log likelihoods. How are we going to use this to derive fit indices? Well, in order to explain this, you have to get familiar with some of the terminology here, and I'm really sorry that there is this terminology, but here it is. And it is as follows. In statistics programs, it's going to give you specific kinds of information in the output. And let's look at some of that information in the output. So if we go to day 1, session 4, model fit, just for a second, I'm going to open up this analysis H0 model, but you don't have to do it yet yourself. Let's just look at what it says in the output. If we scroll down under fit statistics, what is it giving us? Number of free parameters. That means number of parameters it's estimating. How many parameters is it estimating? Look at this. Log likelihood for H0. Some people say HO, don't they? But it's H0, it's H0. At least in the original Neyman and Pearson, what is it, like 1933 paper when they came up with this. Then there's a log likelihood, it says H1 value, and then it gives us a number. So these are log likelihoods. So if we multiply those by -2, we get something that has a chi-square distribution. That's interesting. Or, if you're interested by that. And, oh, this is interesting, chi-square test of model fit. Well, where does that come from? It gives us a chi-square value and a p-value, and it says degrees of freedom 2. Ah. And then it's got these other fit indices. Oh, look at this. Chi-square test of model fit for the baseline model. What does that mean? I don't know what it means, but geez, that's a small p-value. Can we make sense of that? Well, how are we going to interpret this output? What does it mean to us? Okay, so in terms of model fit, there are different kinds of models that have names that we should become familiar with if you really want to understand what Mplus is doing and where the fit indices come from. So I'll give you the cutoff criteria in a second. How small does RMSEA need to be? Or how small does SRMR need to be for me to publish? We'll get to that. But in order to understand what you're dealing with at all, you're going to need a bit more background information. Or you could just go read the Hugh and Bentler discussion section where they talk about the cutoff criteria and whatever else if you want to skip it. Okay. In statistics programs, they'll use specific terms for a specific kind of model. They'll call it the analysis model. Mplus often does that. Or the estimated model. Sometimes you'll see that. And Mplus, it's the H0 model. H0. H0 in Mplus output. And that's our model. That's the model that we specify and estimate. The analysis model. The estimated model. That's ours. That's the one that we drew up there, wherever on the board. It was projected. That's our model. That's the one that we estimate. There's a different kind of model called the baseline model, or the independence model, or the null model. You might say that. And that's the worst fitting model possible, the absolute worst. It doesn't get any worse than that. That's the worst possible model in terms of fit. Or at least, that's a model where it's like modeling all of the covariances among the observed variables in the model as being 0. No slopes, no covariances. So you can't account for any covariance in the observed data. It's as bad as it gets. So we've got the worst model. So we've got our model, analysis. We've got the worst model, baseline. And then we've got one other model called the unrestricted or saturated model. And in Mplus, that's H1. That's the best possible model. It's like estimating all possible covariances and fitting the data as well as you can. So we can get a log likelihood for every single one of those. So if you like your analysis model, which of those do you probably want to compare it to? Well, probably not the best fitting model. You probably want to compare it to the worst fitting model, because your model will look better than that, right? Well, let's see what these fit statistics do for us, because different fit statistics rely on comparing our analysis model to either the baseline, right, which is bad, or the unrestricted model. Okay, for comparison, for comparing models, that we actually estimate, so that's just what the Mplus language, or the stats program language. But if you're doing like model comparisons, you estimate 2 different models, and you want to compare those, like if you're doing invariance testing, for example, which somebody brought up, you want to compare, you want to look at the measurement properties of a scale if it generalizes across cultures. You've got 2 cultures, so you set up a multi-group SEM or whatever it is, and then you want to see if constraining all the parameters to be equal impacts model fit. Well, in that case, you're comparing 2 different models that you're estimating. So we'll see how it works in just one second. But anyway, in that case, we'll use a different terminology. Because now we've got 2 models that we're estimating. They're both analysis models. But if we want to compare them, we're going to give them different names. We're going to say the null model, in that case, which is H0, is the more constrained model. And we'll see what that means in just a second. The parameters we're estimating are a subset, typically, of the parameters we're estimating in a different model. And that other model, the different model, is our alternate model with more parameters being estimated. So again, we're going to run through it. less constrained model, we'll call that H1. So let's check out the analysis model. What does it look like? Well, it looks like that. This is where it's different from all the years prior. We're actually going back to the model that we estimated. Hopefully that helps. So if we look at the log likelihood of this model, what is that? That tells us about the fit of this model to the observed data. Or at least it gives us this likelihood value. We can multiply that by -2 and get a chi-square for the analysis model, for the model we actually estimate. In the Mplus output, it's weird, but this is the null model. Now, usually when you're doing null hypothesis significance testing, do you want to reject the null? You want the p-value to be small, right? That's how you get famous, is you want to go with the alternate hypothesis. But when you're doing model comparisons, typically the opposite is true. Your model is actually the null model, and you don't want to have to reject it. So we'll see why in just one second. The df in this model is the difference in the number of estimated parameters and the number of observed parameters implied by the data. So how many observed parameters did we have in the data? K means whatever the number of variables we have, that many means, that many variables, and k times k minus 1 divided by 2 covariances. So when we subtract the number of estimated parameters from that number, whatever that is, given the number of observed variables, that gives us our degrees of freedom. So if we go to the Grandian I really should choose a different article because I've never been able to say that felicitously in these talks. So if we go to the Grandian-Crapanzano model, our output, when we look at it, now we know, what is this? H naught. That's the log likelihood associated with our model that we've estimated. That's the Grandian-Crapanzano model that we drew up there on the board. But why do we call it the null? That's a little weird, isn't it? Dude, it's so weird. Okay, so why is that? Well, if you think about what a null hypothesis is in, let's say, a regression model, right? So you're estimating a slope, and what's the null hypothesis in relation to that slope, estimated slope? Sorry? Right. Well, the null hypothesis is that that parameter is 0, that the slope is equal to 0. That's what makes it the null, is that something is being constrained, something is being restricted. The estimated parameter that you've got under the null is 0, typically. It's the nil null, right? So, why are we calling this the null? We call it the null because in relation to the next model, the unrestricted model, the saturated model, where every possible covariance is being freely estimated, which is the more constrained model? Which is like having the slope restricted to 0 and calling that the null? Is it this one, or is it our analysis model? This is the more constrained model. How many arrows do you see? How many paths? 1, 2, 3, 4, 5, 6, 7, 8. How many paths do you see here? All possible covariances. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So which is the null? Which has fewer things being estimated? Just like the null hypothesis for your slope is 0 versus your freely estimated lovely alternative that you want. You want it to be non-zero, so you can publish it. But in our case, our null model, not parameter or hypothesis, the null model, we'll say, is our analysis model or estimated model. Because when you compare it to a model that has everything estimated, it looks like ours has fewer parameters. So this is the alternate model. Okay, so this actually sets up a little bit of a conundrum, doesn't it? Because do we like our analysis model? Let's say this is your thesis, or this is your whole career. Your whole life, professional life, has been based on walking around telling everybody, look at the rules by which the world operates. Here they are. Work-life distress, or whatever the heck it is. You know, that's your career. Do you want to reject this? Not if you love it. You don't, unless you're like, you know, you got some attachment issues and... Yeah. But that's why you got into psychology to begin with. It's being recorded, I'm sorry. Okay, so it's funny because it's true. So here we go. Do you want to reject this one? Well, no, not if it's the thing that you want to publish, you don't want to reject it. When you're just looking at regression coefficients, yeah, you want to typically reject the null because that allows you to say you found something. But when it comes to this, our analysis model, you don't want to reject it. We don't want to reject the null. What are we comparing it to? It turns out that we're comparing it. The alternate model is this best possible model. Is that a fair comparison? This is going to fit the data as well as any model can, because all the covariances that are actually in the observed data, they're being estimated, freely estimated. No degrees of freedom in this model, because we're estimating just as many parameters as are associated with the observed data. Well, that's not a very fair comparison. Anyway, what do you think is going to happen? Okay. This is like saying, when you get the log likelihood of this model, let's go back to the Mplus output. This is like saying, look at that, H1 value. That's the log likelihood associated with that other model, that unrestricted or saturated model. What is this number? Negative 4356. Multiply that by -2, you get a chi-square value. Okay. Now check it out. Let's estimate that model. If that is our analysis model, then what should we see when we estimate it? We should see these two things be exactly the same. Does that make sense why? Because the null will be the saturated model, which we're estimating. And let's open up this file and you'll see how it works. Grandi and Cropenzano unrestricted H1 model.imp. Unrestricted H1 model. And let's look at what the input looks like. Look at that. What does that mean? All the variables with all the variables. Estimate every possible covariance. Okay, so that's going to fit the data as well as any model can. Is that very useful? Does that help us make plans for action intervening in the world? No, just a bunch of non-causal, just a blob of all the variables. But for helping us understand where our fit statistics come from, we're going to compare our estimated model actually to this one to get chi-squares. Watch. So when we run this, if we go down and look at the null H naught log likelihood, which is the estimated model, it should be exactly the same as the H1 log likelihood value. Because when Mplus gives you the alternative H1 value, that is the log likelihood of the best possible model. So in this case, those are the same.
Why are they different from this version to the previous?
Oh, I'll tell you why, because I stupidly...
It's missing a variable or something?
Yeah, there's something in there. I don't know what I've done. Oh, that's why. I think it's because we're using this. I've generated some fake data based on the original data, and so I think we're using that for this because it's going to come in handy later. But it doesn't matter. The whole point is that the saturated model, the best possible fit, if you estimate that, then these values H1 and HO become the same because H1 is the best possible fit you can get. So just know when you're looking at your analysis model, let's go back to the other analysis input. Yeah, good question. I realized that too. I was like, oh god, what's happened? We can switch it so it's using the old data, and then it would be this value. Good God, all the little things. The H1 value is the best possible fit, and the H naught value is the fit of our model, the log likelihood. Okay.
Can I ask about parameter numbers?
Yeah.
In your saturated model output, it says there are 20 being estimated.
Yeah, and that's why the fit is all screwed up, because it actually has all the other
So
variables.
If it was ideal, there would be a 2 parameter number to match the degrees of freedom on the chi-square.
Yeah, exactly. In this case, we have 16 estimated parameters. The degrees of freedom is 2. You add those together, and that's the total degrees of freedom given in the observed. That's the total number of parameters associated with the observed data. Yeah.
Is this not the same thing with the RMSEA reset test?
Sorry.
Is this the same thing with RMSEA reset test?
What is it?
RMSEA reset for functional form of association.
RMSEA who?
RMSEA.
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 RMSEY. Oh, I don't know what that is. We have an RMSEA value, root mean squared error of approximation. Is that what you're thinking, or something else? You said RMSEA.
Yeah, it's for like for functional form of association. This is about like
Okay.
test for the functional form of the model. So I wonder if it's the same thing with what you're trying to do. Because it's also
Ramsey is in the famous statistician Ramsey,
yeah.
like 1920s. That guy?
Yeah.
So sad. He died at like 28 years old or something. He was super brilliant. I don't know what the test is that you're referring to, but if it carries his name. But anything that you want to do with the log likelihood, this is the log likelihood associated with the model. So if you want to do something with that, that's the log likelihood of the model.
Yeah, it's the same thing that's an ask because it's just the same procedure.
Okay. Yeah, I mean, again, all of the statistical information used across fields is typically common and similar, and the names for specific kinds of tests might differ, but you let me know if it's the same when we do a test in a second. Okay. So let's... So what does our baseline null or null model look like? So if we want to diagram these models, we have our analysis model, it's the one we were familiar with. We've got the saturated model, or the unrestricted model. That's got all possible covariances. And the baseline, or null model, might look like this. No covariances. This is the worst possible fit to the data, isn't it? Because it's not going to explain any of the observed relationships among the variables. This is as bad as it gets. This is as bad as it gets. So should you stand next to this one, or should you stand next to this one to look good? Probably want to stand next to this one. Okay. This is the worst possible fit. No covariances are being estimated. The degrees of freedom is the number of observed covariances which are not being estimated. So we've got a baseline model there, and you can go look at it. And in fact, how do we do that? Let's go into baseline model, open it up. Now look at the model statement. Not a lot of there, right? Nothing. It's saying we're just agnostic about how they relate to each other. We're just a little fickle, you know? We wanted some slopes, we wanted some covariances, we didn't know, and let's just run this one. Okay. So let's see what the output we get. Let's see what it looks like. So we'll go down. So this is the worst possible fit given the data. This is the best possible fit given the data. I've obviously screwed this up a little bit because we're referring to different data sets. But it's okay. When we go back to the analysis model, it's going to be fine. Okay. Here's what I want you to see. Just one second. Chi-square test of model fit for the baseline model. That compares that compares or it just tells you the fit of the worst possible model. It gives you the chi-square of the worst possible model. Now let's look at so what's that value? 1993. Great year for music. It was. What is the fit of our model? Same thing, because we're estimating the worst possible model, the baseline. If you want to diagram it, it looks like this. Okay, so now you've got diagrammatic representations of the three different models. Your analysis model, which is, I know it says null up there, but that's because like there are no covariances estimated. It's all confusing. I'm sorry, there's overlap there in the terminology. It's just the way it is in the literature as well. We have our analysis model, which Mplus gives us the log likelihood of as H naught. And then we have the best possible model, and Mplus gives us that likelihood value, the log likelihood is H1, which is like the alternate. And then we've got the worst possible model, or baseline model, and Mplus is giving us a chi-square for that. So how is all this relevant? How do these models feed into fit statistics? We'll check it out. Let's look at the absolute fit index. And this is our model chi-square. So what is this? Well, let's find it in the output. It's not the log likelihood, but it is based on it. So let's go to the original analysis H naught model. When we scroll down and find model fit, we go past the log likelihoods, and we find the chi-square here. Well, what is this telling us? 16.603, p less than 0.05, definitely. Even 0.01, whatever. Well, what does this mean? Where is it getting that number? Check this out. What's the difference between these two values? Multiplied by -2. 16.603. So here's what it's doing. It knows that log likelihoods have a chi-square distribution if they're multiplied by -2. So if you multiply each one of these by -2, and then subtract our lovely model that we don't want to reject, the H null model, we get rid of fit of the other one, which is the best possible model. What we get is our chi-square. So we can do null significance hypothesis testing on our analysis model because the log likelihoods have a chi-square distribution. You multiply them by -2. And if you subtract one from another, that has a chi-square distribution. And so that's where this chi-square value is coming from. What does this small p-value mean? What's being rejected? Small p-values mean reject the null. Which model is the null model? Our analysis model is H naught, right? So we have to reject H naught, which is our analysis model. Oh my God, the world is now upside down. Because before we wanted we wanted small p-values, we wanted to reject the null because that meant we had a significant finding in relation to a slope, a regression coefficient, right? So overrun. But in this case, rejecting the null is like rejecting the whole model. It's like rejecting our analysis model. Well, where does that comparison come from? That comparison comes from a contrast of our analysis model. So you know, from our analysis model compared to the best possible model. Is that fair? Yeah, hell no, is what you're that's what you're supposed to say. Yeah, no. We might say no. We don't think that's a fair comparison. That small p-value, what is it going to lead us to do? We have to reject the null. The null is our analysis model. We want to keep this model. We want to publish this model. So what are we going to do? Well, guess what? The SEM community has a solution to this problem. They're quite precious about their models. And justifiably so, right? It's your career. So what are you going to do? This is a comparison. That chi-square value, 16 point whatever it was, that is a contrast between the model that you estimate and the best possible one. that will quite often be statistically significant. Quite often. The degrees of freedom there is the difference in the estimated and the unrestricted model df. If our model is good, the difference should be small, right? If our model really explains the data well, then it should be just as good as the best model. Maybe. Well, what happens to p-values as sample size goes up? Right? So what could happen is you could have a very small sample size and you could fit your analysis model to the data and the p-value is not small. So you don't have to reject your analysis model. But if you have a huge sample size, what's going to happen to that p-value and that chi-square? P-value is going to go down. All of a sudden you have to reject the model that you love so well. So this is kind of weird because in this case you don't want to reject the null, do you? Because the null is your model. What a pain. When you go to, see, the frequentists are just addicted to this null hypothesis significance testing and the p-values. So they give this that kind of a meaning. After the information criteria and the Mplus output, that's the chi-square value. Your model versus the best one. It's all the time going to be small. That p-value is almost in every case small, which would lead you to reject your analysis model, the model that you're actually estimating. So what do? Here's what happened in the 80s and 90s. The SEM community got together, and in a series of articles, they kind of collectively agreed that they were just going to ignore the chi-square value for the most part. And there are still some purists who were like, yeah, but that's a sound statistical footing. There's sound statistical theory underlying that test. You have to use that. And everyone else is like, yeah, but we can't publish our papers if we use it. So what kinds of logical tools can we bring to bear on this problem to discount that small p-value and that chi-square? And here's what they say. They say, oh, that test is sensitive to sample size. Everyone knows that. So as your sample size goes up, and you should have a big sample, right? That's good science. Right? Well, if the better your science gets, the less able you are to do your science, what are you going to do? Well, something has to give. So you have to discount that chi-square value. So it's rarely taken seriously, unless what? Unless it's greater than 0.05, that p-value, and then you say, right, it's just as good as the best model. Look at this. And so you will see that. In published papers, if the p-value is larger than 0.05, they'll say it's so good, we don't even reject it. That's how good it is. But the weird thing is here is that in this case, strange, you want to accept the null. Because the null is your model. Ugh. Yeah.
The idea that you want the most parsimonious model you can come up with, even though you're not model building, you're actually starting from spontaneous driven, it's hypothesis driven, you're coming up with a model based on your ideas about things, or still, we're in this passionate love affair with parsimony, or parsimony.
It's a lovely root vegetable, parsimony. But exactly. So the thing, though, is that, I mean, the idea there would be that the way additional degrees of freedom modify that p-value is not enough, right? So as your model becomes more parsimonious and you're estimating a few parameters, degrees of freedom go up. But what that doesn't do is adjust the p-value, basically. You think about it like this. It doesn't adjust it enough. So what do we want to do? We want to come up with a way to use chi-squares and degrees of freedom and whatever, and just overvalue
Why don't we just do it like Bonferroni?
parsimony.
Just use division. You know?
Well, we've got other tools. So here's what they do. If you want to look good on a relative basis, here's what you do. One thing you can do is compare your model to a different model that you've also estimated. So you're no longer looking at the chi-square, and you're no longer comparing your model to the best possible model. So they make this recommendation in the SEM community all the time. They say one thing you might want to do is have two different models that you're estimating and compare those and look for changes in fit. When you go from one model with more parameters estimated to a model with fewer estimated parameters. which model is the null model in this instance? Null always means less. Null always means fewer, right? The null hypothesis for the slope is that slope is 0. It's not being estimated, right? You think about it like that. So in this case, we can estimate both of these models, and we can get chi-square values. It'll give us those chi-square values, and we can subtract the degrees of freedom and subtract the chi-squares, and now we've got a little chi-square test of this versus this. This is the null model in that chi-square test. So if we see p less than 0.05, we reject that one, and we go with that one. So some people do that to try and get around the problem of constant statistical significance that would lead you to reject your model. You know, estimate a model you don't like that has a subset of the parameters of a model you do like, reject it, and say, well, sorry, we got to go with this one. Right? I like that one. Okay. So the condition for this with formal statistical significance testing using the chi-square is that one model has to be what they call nested within another one. The parameters that you estimate here in the null model have to be a subset of those parameters. Basically, estimate your model of choice, eliminate some of those that you're estimating, and that becomes the null model. So if you want to do model comparisons, essentially that's what you're doing. In the case of multi-group invariance testing, you've got a model with lots of freely estimated parameters in two groups, and then you restrict those to be equal to each other. That's like a subset. And then that one, the constrained model, becomes the null model. And you just compare the chi-squares. Same kind of logic. Yeah.
Which of the nested models you have?
Yeah, I don't know. We'll get to that at the end. So there are a wide variety of different ways that you can do that. It's got to be based on what people in your community are going to think is reasonable. Yeah. But there are a couple of different procedures. Yeah.
But to do that, you still have to have a good rationale, right?
Yeah, exactly. Yeah, exactly. So we'll talk about where that rationale might come from in a second. So null hypothesis significance testing with these likelihoods or these chi-square values, if you want to get into that kind of thing, there is a big literature on it. It started kind of formally in a modern sense with this famous paper by Neyman and Pearson in 1933. They actually used the H0, H1 notation. And it's often called likelihood ratio testing because you don't have to multiply those things by -2 and subtract them. You just divide them by each other. So some of the shortcomings here, this requires nested models. The parameters in one have to be a subset of the parameters in another. With large samples, it can often make people unhappy, right? If you don't want to reject one that has the fewer parameters. I mean, in the case of invariance testing, you don't want to reject the null model. You want to say, hey, look, the measurement parameters are the same in the two populations. So that constraint of making the factor loadings or whatever it is equal across the two groups, you don't want to reject the null. Well, if we want to get away from this logic, there are a couple of different options we have. And let's develop and use some fit indices that treat us a little better, that could be friendlier to us. And all the other fit indices that Mplus reports can be useful for this kind of thing. So one of the things that Mplus reports is the SRMR, Standardized Root Mean Square Residual. So this can be thought of as, so let's find what it was for our model. So in the analysis model, the p-value was less than 0.05, less than 0.01 even. Looks like we're not going to be able to publish it, right? Let's scroll down here. What's that say? It's not false. 0.02. Well, let's give that an interpretation and apply a cutoff to it and see if we like that one better than that small p-value. You can think about this, the SRMR as like the residual correlation among the observed variables that your model can't explain. So it's like if you take your model and all the estimated parameters and all the observed and the correlations among the variables implied by your model, and you subtracted that from the actual observed correlations among all the variables, what's left over is like your SRMR. It's one way to think about it. It's like the average residual correlation among all the variables. Yeah. Yeah, exactly. The smaller the better. Yeah. Already it's different than a p-value. Right, exactly. The smaller the better. So 0.02 is actually quite good. It's saying the average residual correlation, again, this is one way to think about it, the average residual correlation is only 0.02. That's all we're not explaining with our model. 0.02 is the correlation left over after you account for the correlations implied by the model that you estimate. So Hugh and Bentler, in this famous article, they say things like, hey, if it's less than 0.05, that's pretty good. There are a lot of kind of conditional statements in that paper that we don't have to go into all of them. Then they also make statements like, you know, 0.08, that's not too bad either. Maybe anything bigger than 0.08, and you know, people will cite it all the time, and whether they've read it or not, who knows. It's got tons of citations, like 20, 30,000, or more, whatever. Anyway, so that's the SRMR. Sorry?
So every time you have to justify a marginal fit, that's where you go.
Maybe, you can go there. Is this thing going to be overly sensitive to sample size? No, it's just the residual correlation. So your sample size could be large or small, and this is going to tell you how much is left over unexplained. So that can be useful if you want it. Here's another one, the RMSEA. This is, this makes adjustments based on the number of degrees of freedom to value parsimony. Again, right next to the turnips in the vegetable aisle, parsimony. So the root mean squared error of approximation, it's like an adjusted SRMR, or standardized residual. Basically what they're doing is they're trying to take model parsimony into account. There's the formula for it. You get penalized if you have too many parameters. It's basically a way to adjust for degrees of freedom in a way that's more favorable. So that's it. Hugh and Bentler say, hey, less than 0.06, less than 0.07, that's pretty good. These days, because everybody's so concerned with fit indices and uncertainty in them and uncertainty in the model and everything, it's just, you know, somebody takes something that was initially used as a cutoff or whatever and they turn it into their career. And so now we have confidence intervals for these things. So in psych, for example, you're supposed to report the confidence interval. Mplus gives us this. Let's check it out. So if we scroll up, we find the RMSEA, which is 0.085, and the 90% confidence interval is that, and then they give you a probability value. You can report all of this. So what's the probability that the RMSEA is less than 0.05? Not very high. That doesn't make our model look as good as the SRMR. So when you're publishing this stuff, what do a lot of people do? You can just see it. Open up the journal article, and what do? When they, right in the SEM community, they'll say, oh, but the SRMR is pretty good. You know, we recommend focusing on that. That kind of thing. Anyway, the fit statistic is there. What about other kinds of fit statistics? The CFI, where does the CFI come from? Comparative Fit Index. So what kind of comparisons do we like? We want to stand next to the worst possible model, not the best one. So why don't we use the chi-square of that baseline model, that one that fits the data horribly? So here's an approach that does that. You can see it there in the formula, the baseline and chi-square estimates, the analysis and estimated model. Chi-square and degrees of freedom are there. And again, what we're doing also, though, is we're adjusting the fit, essentially, for degrees of freedom or parsimony. And here they say, right, greater is better, more is better. They say greater than 0.95 is good. Boy, these people, there's such a trend here. 0.05, 0.95. I don't know why they love those values. Why not 0.09 or 0.955, 0.954? Larry David's got this whole thing in that, what's that, Curb Your Enthusiasm, where he's like, somebody's like, let's meet at 3. He's like, no, let's meet at 3:07. They're like, why do we have to meet at 3:07 in the afternoon? It's like, why do we have to meet at 3? It's just as arbitrary as 3:07. Anyway, we like nice round numbers, I guess. So Hugh and Bentler, 0.9. I mean, that's kind of the standard. If we look at our output, what do we see? Are these treating us pretty well? Yeah, so people report those and then focus on them. Are we really helping our case? Let's just move through this because it's so incredibly interesting. If you want the formulas, that's why it's here, some of the underlying logic. The TLI or the NFI, the Tucker-Lewis index or the non-norm fit index, those are the same thing. It's similar to the CFI, slightly different penalization. You can see the formula here. They'll often report these and focus on them, but are we getting any closer to causal inference with this kind of stuff? We haven't really fixed any problems with providing regression coefficients with some kind of causal interpretation or causal meaning. What are we doing if we rely on these fit indices? What are we doing if we rely on these fit indices? Well, we're using these to help us have at least some kind of guide for understanding whether or not we can go into the model output and interpret all of those on statements, the estimates after that. And that's one of the reasons why the fit indices come first in the output, if you think about it. So if we get our output and we scroll down, we have to go through the fit indices to get to the actual parameter estimates, right? We have to go through the fit indices before we can get to the on statements and the slopes and the p-values and everything else. But why do we have to do that? Because remember this idea for a maximum likelihood estimate, it can be the best estimate that you can get, but still not explain the data very well. It could still, the model you estimate could still fit the data very poorly, not explain the observed patterns in the data, and you can still get results. So before you go down to the results, what Mplus is doing and what the community of researchers, what they want you to do is they want you to make kind of a general assessment of whether or not your model is justified in terms of the data. And so that's what these fit indices are doing. After you clear this hurdle, you know, whatever the cutoff criteria you use are, after you clear this hurdle, then you get to go to the model results. Then you get to go to the on statements and the p-values. But if these fit indices are not good, like if that's 0.5, then what that means is that the average residual correlation that your model can't explain is 0.5. That's a lot. It's like saying your model stinks. So if your model isn't good, why are you interpreting the regression coefficients? Why are you interpreting the covariances that are estimated? Why, you know what I mean? So this is what you do first before you move on to those other things. But look, let's do it here. How do we do it? Well, chi-square says reject the model we estimated. We don't care about that because the SEM community says forget it. That doesn't look very good. RMSEA is 0.085. Should probably be below 0.07 or something. It depends on the reviewers you get. These look pretty good, and that looks pretty good. And so quite often what you'll find in the literature is that based on those findings, they'll just go ahead and keep going and interpret the results and write them up and whatever. So that's just a kind of preliminary backstop to ensure that, or check, to ensure that you haven't done a horrible job of things. But that doesn't really help you make causal inferences or causal claims per se. That's still a function of the data and a variety of other things. But you want to go through that before you get to your regression coefficients. All of these things haven't changed. Still just rise over run, slopes, p-values, unstandardized values, standardized values. Now we're just looking at some of the fit statistics. Okay, there are two other fit statistics, or three others, that are provided there in Mplus output, and they're called information criteria. These aren't very commonly used in the SEM community. They're used quite heavily in, like, you know, time series literature, for example. But you should know that they're there and what they mean and why some people like to use them, or at least a little bit about that. The first one is the AIC, or is it a keiki or a kaki? A kaki? Okay. Information criterion. And this, in fact, was originally developed for the time series case, I think, for assessing fit in time series models. So here, K is the number of estimated parameters, and we have, what we're essentially doing is we're providing a weighting scheme that adjusts the chi-square, the fit, for the degrees of freedom. And this is really not an absolute fit index, so you would never say, oh, if it's below 0.02 or above 0.95 or something like that. Typically, the values that you get here are negative, and the lower the value, the better the fit of the model. And usually what you're doing is you're comparing two different models based on this. And the convenient thing about these information criteria is that it doesn't matter if one model is nested in another. You can compare any models that you like. Lower values are better. And the same is true for the BIC, or Bayesian information criterion. Sometimes it's also called the Schwartz information criterion, the SIC or the BIC. And it's similar to the AIC, except it also accounts for sample size. And then you've also got sample size adjusted AIC and BICs, and you can go look up the literature on that if you want. Smaller values here are better, means better fit. It's like less information loss when going from the data to the model. That's always how I think about it. So the issues here with these is that these are all what we'll call global measures of fit. It takes the whole model and how it fits all of the variables that are used to estimate that model, and it gives you like one value, a chi-square, for example, or an SRMR. But what if one little part of the model fits horribly and the rest of the model fits really well? Well, because these are all global indices, it's just going to kind of average across the fit all the different spots where local fit could be good or bad and give you one value. It collapses across all model parts. So some authors call for separate fit indices, and we'll see when we start doing SEM and CFA on Wednesday that we can get separate assessments of model fit for a kind of measurement part of the model versus a different part of the model. But anyway, you should know that that's an issue here and that some people talk about that. Whatever. The point is that model fit is a necessary but insufficient condition for making things like causal inferences. Arguably, if your model works well, then, or rather, arguably, if you're going to use the parameter estimates to make causal inferences, then the model shouldn't have a horrible fit to the observed data. It should at least be able to explain the observed data relatively well, if it's a good model. But that doesn't mean you can make causal inferences. It just means you can proceed down to the reported regression coefficients and then encounter the problem of whether or not you can make causal inferences based on your observed data, etc. Okay. Okay, we just talked about that. So, what about modification indices? How many of you have heard of these? These are quite common, and Mplus will report them for you if you want. It's a neat little trick for finding little areas of local misfit in the model. Basically what Mplus will do, and the underlying logic of a modification index, is Mplus will tell you about the change in model fit you would get if you estimated some parameter that you're not currently estimating. So for example, if we go to, let's go back and actually look at this analysis model that we estimated with these data. Are we estimating a direct effect of work-family conflict on turnover intentions? Is there an arrow that goes from WFC to TI? No. That could be a source of misfit. What if there's an observed relationship between those two variables that cannot be explained by the other part of the model? That's going to cause misfit. So what this mod indices command in Mplus will do is it'll tell you how much change in fit you'll get, how much better fit will be if you estimate something that you're not currently estimating. And it'll give you a bunch of different options quite often, and you can modify the way that it does that, but the option is there. And we don't really cover that because, I mean, they can be useful diagnostically, but it leads to cheating, right? Because who's there with you in the room when you look at the modification indices? Probably nobody. Probably nobody reasonable, because you're doing something very boring, right? Right? So you're all alone there, and then you look at these modification indices, and Mplus says, psst, don't tell anybody else, but if you just use another on statement, connecting those variables, it's really going to improve fit a lot. And you know, I don't normally say this to everybody, but I think you should do it and not tell anybody. Right? So now all of a sudden what you're doing, you put yourself in a strange situation where now all of a sudden you're privy to information about how to improve the fit of your model that nobody else is. That leads to cheating. So I think this can be really useful diagnostically and inductively, right, for kind of theoretical reasons. You can say, oh, it looks like there's a relationship there that this model, which I like, can account for. I wonder what would produce that. Is it just sampling error variance? Is it noise? Is it, who knows, right? And that's the problem, because now all of a sudden that very quickly leads to overfitting, where you're just estimating all kinds of stuff that has no strong theoretical rationale, etc. So these can be useful, especially in the very beginning, like in a multi-stage process of fitting models to different sets of data. In the very beginning, you might want to work more inductively, or split your sample in half and estimate a model on one half of the sample, right? And then look at the modification indices and use any that you think are reasonable, and then whatever that final model is, apply it to the other half of the data and see if it works well there. That's a reasonable way to avoid too much cheating. Because if it's just noise and the sample is randomly divided, then it should be fine, an infinite number of times, in theory. Okay, so there are a lot of debates here, obviously, about that technique and approach, because it can lead to overfitting. And anyway, you can look it up if you want. The point for Mplus is how to get these fit indices. What is this? And Mplus, the command is really easy. So just like anything else, there's a lot to know about it, and you can read a lot of the literature on it. Let's go to modindices.imp, and if we scroll down, it's basically the same thing except this. Now we've said, hey, Mplus, give us modification indices, and the parenthetical afterwards says, give us modification indices that improve fit by 1 chi-square value or more. And then if you run it, and we scroll down, sorry, I'm going very quickly, I apologize. I'll go slowly. We're going to scroll down through all the results until we find mod indices. And you can see what this is and how it... Model modification indices should come with a warning, can lead to overfitting. Watch out. Modification indices for direct effects, blah, 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 regressive covariates may not be included. Oh, I didn't know that. That's interesting. Okay, it doesn't matter. That's not our point here. The minimum value for printing the modification index is 1. That was the parent, that was the in the parentheses. Okay, what are the on statements that we could set up? Well, what haven't we estimated? That was that, what is it, WFC and TI or something? So we should see TI on WFC. Well, what happens to the chi-square if we estimate that? This is like expected percent change and etc. But let's just focus on this. What happens if we say TI on WFC? Watch how easy it is to cheat. Edit, copy, close that, paste. Now let's see what happens to the fit index, the chi-square, which was previously 16, or whatever it was. What happens to it now? Hey, I know a guy who can get you good fit indices. So now you're cheating, right? And look how easy that was. So obviously this is going to be quite contentious. So again, this is more diagnostically useful than anything else. This is the whole point of this kind of open science initiative, is that behind closed doors, people have been doing this, this kind of thing for years. But look what happens to the p-value. Are we rejecting our model now? No. We're keeping our model. All right. Oh, wow. So good we have to round down to 1. Anyway, so you can see how that works, right? You request the mod indices, but again, to really make this make sense in a hypothetico-deductive framework, to be honest, and act in good faith, and help create a community that has people who can trust each other, which is what every community is based on, scientific or otherwise. You have to be able to trust each other. If you can't do that, anyway, whatever. If you can't do that, you need authority and violence of one kind or another. You do. You absolutely do. And in order to create that kind of community, you can't do this stuff without, like I'm saying, split the sample in half, etc. And then just be honest about what you did.
Actually, if you look at modification indices, there's a covariance statement between work-life conflict and turnover retention.
Oh, okay.
And that theoretically would make a lot of sense. Turnover is not just a function of job stress, but also the work-life conflict.
You give me enough time, I can make anything make theoretical sense. You know what I mean? I mean, and that's true, right? Because it's just reasons. What's theory? Theory is just reasons. Reasons for things. You can come up with all kinds of reasons. And so I'm not saying you're wrong. I'm just saying that it's a slippery slope there. And so just because you can come up with a good reason very easily doesn't mean, I mean, if you're a content expert and this is your preferred model and you've been working with these variables and constructs for years, you can come up with a reason for anything, right? Because you know how to reason with these ideas, with these abstractions. So, but yeah.
The problem is that the original model has a lot of, let's say, multiple linearity issues.
Yeah, maybe. Let's see. I'm not going to disagree with you. Just saying it's useful as just, hey, this is how you get mod indices here. But yeah, I mean, this kind of thing. How did it ever get published? No. With statements as well, you can see with statements are basically they can provide an equivalent improvement in fit, because you're still just getting a relationship there that wasn't previously there. Whether it's a covariance or a slope, you're still estimating something new. Anyway, those are modification indices, buyer beware, caveat emptor, and well, it's also being recorded, so I certainly can't tell you to run out and go use them. That would, but quite seriously, it should be no wonder that there's a lot of debate about that kind of thing. Okay, well, what about if you use a Bayes estimator? Well, if you don't ever do this, then you don't care about this. But if you want to try it out, and we're going to use a Bayes estimator for a couple of different things, you should at least know a little bit about some of the indices of fit that we're getting. Not as well developed here because almost everything is frequentist, and we're certainly not going to solve that in 5 minutes. And it's less obvious how to proceed here because you have both the observed data and model priors. So yeah, it's not entirely clear. And you don't have, for example, a chi-square, which is a frequentist concept. So Mplus does, though, offer a few indices that are useful. So if we go to Grandi, Crapazzano, Bayes, let's just look at the general kind of output that you get, and then we'll just discuss that very briefly. Bayes, open. You can see what we've done here. Don't worry about these things. The most important thing is estimator equals Bayes. We'll talk more about what that means later when we talk about bootstrapping, because that'll have kind of a nice little overlap there conceptually between what we're doing here and bootstrapping. But analysis estimator equals Bayes, and we'll run the model. And then if we scroll down, it'll say, oh, here we go. Model fit. Same number of free parameters, because it's the same exact model, just a different estimator. Now we've got these things, Bayesian posterior predictive checking, using a chi-square, and then it tells you what that is. Basically, you want that to include 0, and I'll say why in a second. And then this p value, posterior predictive p-value, you want that to be small. So, or no, wait. No, you don't. The PSR should be small, and this, on the other hand, let's go back to the slides and we'll see. And then you also get information criteria. Deviance information criterion, Bayesian, the BIC. There is some literature on this. It's rather technical, and some of it's by the program authors. You can go look that up on your own. So for posterior predictive checking, essentially what it's doing is it's comparing the model that you estimate to one, well, here are the steps. You sample parameters from some posterior distribution. That's the way that you estimate. That's the way you do Markov chain Monte Carlo Bayes estimation, is you're like sampling parameter estimates, and you get a bunch of those. And then what Mplus does is it generates some data with those parameters as if they were true. As if they were true parameters. So if the estimates that you get are good, then when you use those to generate data, those data should look like your observed data. That's the idea. And then you estimate the fit of the model using the generated versus observed data. If the model is good, the generated data should fit better or worse about half the time. There should be no difference statistically. It should be like flipping a coin, which one you use, for example. And that's what this posterior predicted p-value tells you. So that should be around 0.5. And as it goes down, it means that your model doesn't fit as well. The data generated from your model, the parameter estimates, doesn't look like the observed data. And if your model fits the observed data well, that should not be true. Okay, so that's basically it. Anyway, there's a number there. Again, you can go read up on this on your own. This is a bit more obscure even than just the Bayes estimator itself, yeah.
So the posteriors come from your weak data, or is it?
The posterior estimates are estimated based on your data in the priors. But then it uses those posterior estimates. It's like taking the Mplus results and using those for Monte Carlo, right? A Monte Carlo simulation that generates observed data based on your parameter estimates, as if that was the truth. So if those estimates are good, the data that gets generated should look like that real data that you have. And if that's not the case, then that thing goes down. And then there's this DIC. Again, these are just information criteria. This one gets used in specific ways when you play around with your posteriors. So the Muten and Asperohov have some papers on that. You can look into that. Again, it's slightly more obscure. And if you're not going to use a Bayes estimator ever, then why would you care? But if you are, and I think it's kind of going in this direction, then you can look up, do some reading on that. Okay, so model selection, and then we'll go. So how do we actually get the models that we estimate and try to publish? Well, how do we choose these things? Well, how do we select models, for example, just when we're estimating them and looking at fit and whatever else? We can build them based on scripted steps, like start from something that's really complicated and work down, or start from something simple and work up, or some literature says do a multi-step, right? There should be a multi-step process where you Sometimes it should involve comparing different models that are more or less plausible and look for differences in fit, etc. In general, typically what people do, obviously, is they have a preferred model and they do various things to try and rig the system so that they can publish that preferred model and whatever. If you're going to do that, just try to be as honest as possible about what you're doing and let the reviewers decide if they're going to be agreeable to that. Again, that's the only way to develop a trusting scientific community. But go into your literature, your relevant literature, build different models that you think reviewers would say, okay, yeah, well, we think all of these are relatively plausible, and then you can run all of them and look for differences in fit, for example, that kind of thing. There are papers on this. There's no one single right way to do it. And that's the problem, right, is that you can specify any model you want using on and with statements. Just reverse the order of variables. There's no one best way to do that. So then I would say, and I'll only say this once, I would say that this actually implies some pretty serious ethical issues there. Because what do people use scientific results and findings to do? Well, some people use them for all kinds of horrible things. I mean, the history of statistics is not nice, right? And I don't just mean getting kicked in the face with a horse. I mean, right, by a horse. I mean, historically, a lot of those results were used for eugenics, to justify eugenics. One of the first published regression analyses in the late 1800s used this technique, regression, and the method of least squares, borrowed it from astronomy, and used it to justify reducing the dole in the UK for people who were very poor. And it said, it makes them lazy, it does whatever. And it was just regression. It was just regression with observed variables. So if that's what science is used to do, then the model you estimate really matters. Because once you put it out there, who knows what people are going to do with the finding, right? So if there's no one right, true, or best way to specify a model, then you got to think of maybe a little bit ahead. Say, the idea of achieving some kind of abstract truth at that point is gone. So then what do you have? Well, you have practical considerations like ethics. So that's all I'll say for that. But there are some papers there that you can look at on that point. Don't worry, if you liked all of the path analysis stuff and the on and the with, and it felt really good, and then this stuff is like kind of confusing and less relevant, that's fine. If you feel that way, I feel obligated to cover this because you're going to have to talk about fit statistics and report them. And if you get some critiques by reviewers, for example, you should kind of know what they might be talking about. Tomorrow we're going to come back, and it's just Mplus, on statements, with statements. What can we do with it practically? And yeah, that's it. So that's it. And see you tomorrow. And one day down. Not bad.